Hello students, now today's topic is Lenz law. We already started about Lenz law. You have heard it in the last lecture of Faraday's law. Okay, what was Lenz law? It was something we had just told about it. I had just given a hint about it when I had kept the minus sign in the formula for Faraday's law. So here we will study what exactly the Lenz law says. First of all, I will read out the statement. The polarity of induced EMF is such that it tends to produce a current which opposes the change in flux that produced it. Means the direction of EMF or the induced current is opposite to what it is producing it. If something is producing it, then the current or the induced EMF tries to oppose it. Or in simple way, I have written that direction of induced EMF or current is always such that it opposes the cause that generates it, or it opposes the cause of generation. In simple terms, if you want to understand, like in simple basic thing, sun kills its own father. Means what is induced EMF? Induced EMF is something which is produced due to change in flux. Induced EMF is something that produced due to change in flux. So what is the direction of that induced EMF or induced current? It will be in the direction that will oppose the change in flux. It will not allow it to increase. What it will do, it will try to reduce the change in flux, or it will oppose. Means sun is killing its own father. Induced current knows that if there will be more change in flux, the more induced current will be there. But what does the induced current do? It opposes the cause. It opposes the generation or the reason for generation of that. So what it does? It decreases the change in flux. Okay. So simple terms, sun kills its own father. How is sun produced? Sun is produced due to its father. But what it tries to do? It tries to kill its own father. Okay, that is just in general term. So before moving, let us understand, before moving that, what you need to do, you need to remember this. If the direction of current is anti-clockwise, which shows that it is north pole, and direction that shows clockwise is south pole, we have already studied in our previous chapter. So suppose here I have taken two conditions, condition number 1 and condition number 2. Here there is a magnet and here there is a coil. Here also there is a magnet and here also there is a coil. Now from the magnet there will be magnetic field lines. Field lines will be in this manner and it is coming out of north pole. I will draw it over here also. So in both the conditions, magnetic field lines are going inside the coil. Now what happens? We are giving a small motion to the magnet. We are giving the small motion. If it is only in this condition, suppose that the magnet is stable, then there will be no induced EMF inside because the amount of flux is fixed. It is not changing. If the magnet and the coil both are stationary, then what happens? Magnet is also stationary, coil is also stationary. The number of flux that is inside the coil is fixed, that is 3. In here also it is 3. But what causes induced EMF is change in flux, not the flux. What causes induced EMF is change in flux. Means this flux should keep on changing. If I give the motion in forward or reverse direction, both the direction, any of the direction, what will happen? If I give the motion to this magnet in this direction, what will happen? The amount of flux lines that are cutting will increase, because if this goes near, this will also pass through the coil, this will also pass through the coil. And when it goes nearer, the number of field lines that are cutting the coil will go on increasing. Similarly, if I take it backwards direction, in reverse direction, what will happen? Here the number of field lines that will be crossing will go on decreasing. And in both the case, induced EMF will be produced, because the definition of induced EMF is same, that it is equal to the it is only produced when the rate of there is a flux change in flux. Induced EMF is equal to the rate of change of flux. Okay, so here we have two conditions. Now the current that is induced in this, if we give the motion in this direction to both the magnets, then there are only two conditions, that is the direction of induced current or induced EMF. Either it will be in clockwise direction or either it will be in anti-clockwise direction. So suppose we take both the cases. Suppose in this there is anti-clockwise direction, the current is in anti-clockwise direction, which means that it shows north pole. So here it will be a north pole and here it will be south pole. For second one, we take clockwise direction. if we take clockwise direction, here it will be not clockwise, here it will be south pole, here it will be north pole. Okay, here this is north pole, so I have shown north pole, and on the opposite side it will be south pole. Okay, so now what happens over here? There are two conditions. Suppose we take first condition as this, second we take the second condition before. So what happens if I have kept the magnet and given a small motion to that magnet? I have given a small motion to that magnet, and suppose the induced EMF in that, due to the motion there will be induced EMF as the flux line will change. The induced EMF is in this direction, that is clockwise direction, so this will be the south pole. So now what happens when I have given the force? Here it is north pole, here it is south pole. So between two different poles, what will happen? It will try to attract each other. So if I leave the force, if I stop pushing it, then also it will get attracted towards the south pole because of this different polarities. Sorry. So because of these different polarities, it will go on moving. It will keep on moving because south pole and north pole will attract each other. Which means that even though I have left the force, it will keep on moving, and when it will produce infinite amount of energy. Even though I have give, what we did, we kept a coil in the other end of the room and the magnet on the other end of the room, and then we gave a small motion to it. So after a small motion, what happened? It kept on going forward because of the attraction force with the south pole. So what will happen here? There will be infinite source of energy will be produced. Infinite source of energy. एक बार धक्का मार दिया, फिर कभी धक्का मारने की जरूरत नहीं है. We never require to push it once again if we have already pushed it, if the direction of current produced is this. But is it possible? Because of conservation of energy, there is nothing such as infinite source of energy. There is nothing such as infinite source of energy. This contradicts the conservation energy theorem. Here I have read it is based on conservation of energy. अगर आपने कोई फोर्स दिया है, you need to keep on giving the force or something will be repelling it. But here एक बार दे दिया तो फिर आपको फोर्स देने की जरूरत नहीं. अगर ऐसा होता तो कितनी सारी चीजें ऐसे ही चल जाती. आपको मैंने एक धक्का दे दिया, you will go on rolling for distance and distance. तो अगर कार है तो कार में भी फिर पेट्रोल डालने की जरूरत नहीं, एक बार पुश कर दिया. अगर कोई इलेक्ट्रोमैग्नेटिक है, it will pull and keep on pulling. So it is not possible. It contradicts this theorem. Okay. So so this is not possible. Okay. Similarly, here we'll take the second case. Second case में क्या हो रहा है? We are doing the same thing. उस कोने में coil को रख दिया, इस कोने में magnet को रख दिया. Then we started pushing it. As soon as we started pushing it, the electric field line or the flux inside the coil was changing. So due to that, there was induced EMF in it. So due to induced EMF, what will happen? It will create or it will act as a magnet. Here it will be north pole, here it will be south pole. So यहाँ पे क्या होगा? North pole and north pole, it will start repelling each other. North pole and north pole will repel each other. So क्या होगा? हमने थोड़ा force देके छोड़ दिया, then it will थोड़ा आगे जा सकता है, but it will stop because of the repulsion force. Because of the repulsion force between two north poles, it will stop. So what will happen? You need to continuously give some force so that it can move towards the direction of coil, so that if it keeps on moving, it can produce the induced EMF. If it stops moving, then there will be no EMF, as we have discussed in the starting of this lecture. So this motion is very much required. If there is no motion, there will be no induced EMF. If the motion keeps on continuous, then there will be some kind of EMF. So here what happens? It will repel each other. It will repel the cause. What is the cause? The movement of the magnet is the cause. Movement of the magnet is the cause of producing EMF. But what this does? Because of this induced EMF or induced current, there are north pole and south pole acting. And what does this north pole do? This north pole repels this north pole and tries to stop the magnet from coming. And it stops. So क्या होगा? जो प्रोड्यूस कर रहा है, because of this motion, this induced EMF was produced, but that induced EMF tries to stop this magnet at this position only due to repulsion. And if once this magnet stops, there will be no more any induced EMF or induced current inside it. So which means that the direction of, so first of all, this condition is correct because it acts on conservation of energy, and it follows this law also. The direction of induced EMF is always such that it opposes the cause of the generation, opposes the cause of the generation of that induced EMF or induced current. Okay students, I hope the Lenz law is very clear to you. We might be doing some examples in the later on lectures. Thank you students. Till that, keep studying. Have a nice day.